Any general questions, problems, anything? On the list of reminders, um, the first project update is due next week. So if you haven't started looking for a reaction, now would be a good time. There are LA sessions between now and when that's due. If you have questions that you want to broach with the LAs, they should be able to help you decide what works. Any other general issues? Okay, we started talking about kinetics, and again, it's really just an issue of putting a time base to my reaction. Since my reaction is all about moles, 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 right? It's logical to declare the rate in terms of the change in moles per second. And so that is normally what is done, as you'll see that sometimes has slight variations in units. But in the end, it's always some version of moles, 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 right? And we talked about the fact that A, B, and C, because of the stoichiometry different, technically each have different rates at which they're coming or going. And because some are coming and some are going, right, some of the rates are positive and some are negative. So to avoid confusion, right, the rate of reaction is defined differently than the rate of any of the individual constituents. In fact, the rate of the reaction need not be the actual rate that any particular compound is reacting. It's designed to be independent of product and reactant. And so it's always a positive quantity, and it's defined as being independent of stoichiometry. And so it's really achieved by dividing out the stoichiometry of any of the actual measured rates. So really you're measuring this, right? Because you're either monitoring the amount of A, B, or C. Those are the real actual molecules in the reaction. But the rate of reaction is really defined in terms of the reaction as a unit and not the actual amount of any particular constituent. If you do that, whether you measure A, B, or C, right, by the time you turn it into the rate of reaction, you get the same number, right? Whether I measure A, I get 1 per minute here. Whether I measure B, I get 1 per minute, or whether I measure C, I get 1 per minute. All right, and down below here, I get the same number again, whether I measure A, B, or C. However, you might note, as someone did on Wednesday, it is no longer 1 per minute. Okay, and of course, the reason for that is because the rate of a reaction is not terribly useful because it is not constant, right? In fact, most of the next week we'll talk about why it's, or what it depends on in gory detail, right? But the most obvious way to think about it is at some point I run out of stuff, right? If you think in terms of a limiting reactant problem, I'm either going to run out of A or I'm going to run out of B, at which point the reaction stops happening, which means the rate goes to 0, right? And in fact, it gradually slows down until eventually it gets to 0, right? And so ultimately, the rate is the thing I measure, but it's rarely the thing I care most about because it's not a constant, right? And so, right, I'm going to measure it for some individual molecule. And since it's a reaction and it's all about moles, right? What I really want is some version of the change in moles per unit time, right? Because we're mostly talking about aqueous solutions, that frequently gets translated into molarity instead of moles, because after all, molarity is just moles per liter. And if I'm doing the reaction, everything's in the same solution, right? I don't have a beaker of A and a beaker of B and they're separate. And so molarity is directly proportional to the moles because the liters are constant. And I don't need it quite yet, but it's also worth pointing out that pressure right, is directly proportional to moles also. So in terms of gases, the rates are sometimes measured in the change in pressure as a function of time, right? But ultimately, those are just slight unit variations on my main strategy here, which is to monitor the change in moles of something and then correlate that to an actual rate for the overall reaction. And so that problem, well, maybe I shouldn't skip it, right? Really just gave me a actual reaction instead of A, B's, and C's, right? And so the good old Haber process, right? It's an all gas phase reaction for the production of ammonia. It has 3:1:2 stoichiometry, right? And I asked the question, if I mix 3 moles of hydrogen with an excess of nitrogen, and I find it takes 24 minutes for completion of the reaction, what is the rate of reaction? In fact, all of those choices are legitimate rates for what's happening here, but only one of them is technically the rate of reaction, right? It tells me I have 3 moles of hydrogen in excess of nitrogen. What that's really telling me is hydrogen is the limiting reagent, right? And so during the course of the reaction, all of the hydrogen reacts, and it apparently took 24 minutes. Right. And so again, because the rate is always the change in moles, right? I end up with 0 moles, right? That's the final amount because deltas are always final minus initial. And it took 24 minutes for that to happen. And so the rate of reaction of hydrogen is technically negative 0.125 moles per minute. Right. I will point out, because this is an issue on the OWL homework, and it's an issue just in terms of talking kinetics, that minus sign sort of comes and goes. Right? If I talk directly about the rate of reaction of hydrogen, because it's a reactant, it's going to be negative, right? You're losing the reactants. But if I refer to the rate of hydrogen loss, right, essentially the word loss actually implies the negative. And so you will sometimes see in life and OWL homework, right, that the rate of hydrogen loss is expressed as a positive number because the negative is included in the question loss. Whereas if I directly reference the rate of reaction of hydrogen or nitrogen in this case, because they're reactants, they should be negative. Right. Technically, from that, I can calculate 3 other rates, right? Because from stoichiometry, if I know the rate of hydrogen, right, I also know the rate of nitrogen and the rate of ammonia. And of course, I also know the rate of reaction because they're all just a stoichiometry away, right? And so it's really just a question of the relative moles. If 3 moles of hydrogen reacted by stoichiometry, I had to have made 2 moles of ammonia per 3 moles of hydrogen reacted. Look at my beautiful units, and how very descriptive I've made them. I will always put in a pitch for units, especially very specific units, because everything in that first calculation is moles. If I don't specify moles of what, right, it's not at all clear that anything cancels in what I get. Right, and so if I reacted 3 moles of hydrogen, I must have made 2 moles of ammonia. That is technically 2 moles of ammonia minus 0 initial, right? But I made 2 moles of ammonia. It still took 24 minutes, right? And so the rate of ammonia production is a completely different value than the rate of hydrogen loss. It's 0.0833 moles per minute instead of, what was it, 0.125? Right. And I can do the same thing with the nitrogen, right? Because now it's 1 to 3 stoichiometry, right? And so if 3 moles of hydrogen reacted, 1 mole of nitrogen must have reacted. And again, it still took 24 minutes, right? All 3 of those rates are not actually the rate of reaction, right? They are the rate of specific constituents in the reaction. But like when we were talking about good old ABC reaction, if I chose to measure hydrogen, I get that number. If you chose to measure ammonia, you get that number, right? They're not the same number, even though they're the same reaction because of the stoichiometry difference. So the rate of reaction is defined as the stoichiometry independent number. So all I really need to do is divide by the stoichiometry, right? So if I want the rate of reaction, I take the rate at which the hydrogen is changing and essentially divide it by 3. I sometimes write this, it's a weird unit, as 1 reaction, right? Or 1 mole of reaction per 3 hydrogen, right? Because I'm now looking at the whole reaction unit happening, right? But in the end, I'm dividing by the stoichiometry. Absolute value, the rate of reaction should always be a positive number. And so if I do that with any of those 3 measured rates, I get the same number for the rate of reaction, which is 0.0416. The question was, would the reaction coefficient always be 1? The answer would be yes, right? Because it's 3 hydrogens per reaction unit. It's 1 nitrogen per reaction unit. The stoichiometry you see in the reaction is always essentially per 1 reaction unit. All right. And again, you know, to actually do that in the lab requires that I be measuring the concentration of something, and I get this fantastic number, and nah, right? Because the problem with that number is it's very specific to what I did, right? For a couple reasons. One, right, as I mentioned at the end of the ABC discussion, the rate of the reaction is not constant in time. And the reason it's not constant in time, right, is because the concentrations aren't constant in time, right? Because if you think about the reaction, again, in recent years, I've taken to calling, you know, molecules dumb things, even though I mostly like to make them friendly, right? Molecules just run around bumping into things. If you want hydrogen to react with nitrogen, they have to find each other, right? When there's less of them in the same beaker, it's harder for them to find each other, right? And so in most cases, dare I say almost all cases, right, reactions are constantly slowing down because you're losing the reactants And as a result, it's harder for them to find each other to do the reaction.
I have a question.
I have an answer. Let's see if they match.
Is the rate of reaction always fastest at the beginning and slowest at the end?
Yes. The question was, is the reaction rate always fastest at the beginning and slowest at the end? The answer is yes.
Wait, what about like explosives that are extremely exothermic, and the exothermicity of their initial reactions causes like a cascading effect?
Well, different issue, right? The concentration change causes the explosion to slow down also. In terms of the heat, wait for 2 slides, right? But, right, fundamentally, right, concentration matters because it's harder for them to find each other, right? But finding each other is not sufficient, right? In the sense that if hydrogen and oxygen are going to actually react in this particular reaction, they need to find each other. They also have to have proper orientation and proper energy to react. All right. And so the other thing, right, that reaction rates tend to depend on is temperature. Right. And so the problem with any measured number is that it is very specific to the conditions under which I did the reaction. Right. If I start with less hydrogen and oxygen, the reaction will start slower. If I change the temperature of the reaction will get slower or faster because the temperature changed, and therefore the number of molecules that have sufficient energy will change. And so, despite all of my efforts in the laboratory designed to measure the rate, I've measured a somewhat useless number. I mean, it's not useless if that's the reaction you do every day. You know, if every day I show up and I throw 3 moles of hydrogen and 1 mole of nitrogen in a beaker at 298 degrees Kelvin and let it react, then I'm going to see presumably the same rate every day. Right? But if today I throw 4 moles of hydrogen in the beaker and 1 mole of nitrogen instead of 3, I'm going to get a different rate. And so even though I put all of this effort into actually measuring the rate, it's really only a means to an end because it doesn't tell me anything generic about the reaction, right? And so usually measuring the rate is just a gateway to determining the thing I really care about, which is the rate law. Right. As I mentioned last class, we need to be really careful about how we view all of these things that have the word rate in them, because it is very easy to confuse them, right? Because unfortunately, virtually everything we're talking about has the word rate in it somewhere, right? And so a rate law is not a rate, right? The rate law is, however, better than the rate, because the rate law is actually an expression to calculate the rate, which is dependent on the concentration of the reactions and ultimately the temperature, which are the 2 big parameters upon which the rate depends. And so rates are never generic. All right. They're very much dependent on temperature. They're very much dependent on concentration. What I measure was true, but only under the conditions I measured it. The rate law is generic, right? If I construct the rate law for the Haber process, I can then calculate the rate for any mixture at any temperature. And so the rate law is really generally the thing I want, right, when I'm talking about the kinetics of a reaction, right? And I generally get it by measuring the individual rates, right? But the rates themselves are too specific to be useful, okay? And so the rate law is really just an expression to calculate rate. And if I return to good old A, B, and C, right, it should depend on how much A and how much B I have, because as I've already said, they need to find each other, right? It does not necessarily, however, need to depend linearly on the concentration, right? And so we have these things called orders of the reaction, right? In this case, I've represented them in X and Y. They are exponents for the concentration. They're really telling me how strongly the rate depends on the concentration of that particular species, right? The bigger X and Y are, the stronger the dependence, right? Because it's either A or A squared or A cubed, right? And so the bigger the exponent, the faster the rate's going to drop as the concentration drops, right? And it turns out my rate law could depend on A, or it could depend on B, or it could depend on both. As we'll see today, right? Which one it depends on how much tells me something fundamental about how the reaction's happening. But starting from the balanced equation, I can't really know what the dependence is, or even what it depends on. Some reactions, very rare, don't depend on the concentration of anything, right? If you think of, for example, something falling apart, right? If it's just unstable, it doesn't necessarily need to find any other molecule, it just falls apart. In that case, right, I just have a certain probability of falling apart that's not really dependent on what my concentration is, right? But for most reactions, A and B have to meet, and they have to do something. So the vast majority, nearly 100%, but not quite, right, are going to depend on one or both of the reactants, right? And so for the moment, let's assume it's linear, just so I can write something less esoteric than my proportionalities. And so if the rate depends linearly on the concentration of A and linearly on the concentration of B, what that means is the rate should be directly proportional to the amount of A and directly proportional to the amount of B. And so if you think about it, right, if I doubled the amount of A and kept B constant, the rate should double. Right? If I doubled both of them, the rate should go up by a factor of 4. That's what that functional dependence is telling me. Right? Now, the proportionality is great, but that doesn't exactly allow me to come up with the actual absolute rate. It'll tell me the relative rate, right? If I double it, it doubles. If I triple it, it triples, right? But if I wanted to actually get an actual number for the rate, I need my proportionality to be an equality. And so I introduced to you yet another major thing with the word rate in it, which is K, typically abbreviated K, which is the rate constant. This is perhaps the most horribly named of any of these things, because the rate constant is not constant. Right? It's a constant of proportionality, which may be where it gets its name. But in fact, the rate constant isn't constant. In fact, what K really is the temperature dependence. So, you know, in a very limited sense, K is constant. That limited sense being as long as I don't change the temperature. All right. And next week, we'll talk about what that actual temperature dependence is, For now, I'm just going to use it as a specific number at the specific temperature I'm doing the reaction at. Right. But in the end, if I construct my rate law, what I really have is the actual kinetic characteristics of the reaction wrapped up in one simple, easy to use equation that has the two big dependencies in it, right? Right here are the concentrations of the reactants, and K implicitly is the temperature dependence, right? Which is why the rate law is usually the thing I ultimately want, because it's the most generic expression of the kinetics of the reaction. The rates are great, except they're too condition dependent, right? And so usually my whole goal experimentally is to construct a rate law, because that tells me essentially everything I need to know about the kinetics of the reaction, right? As I said, that's already 3 or 4 things named rate, right? I've got the rate itself. I say 3 or 4, right? I have rates of reactions and rates of individual chemical species. So you can almost think of that as 2 different things. Then I have the rate law and the rate constant. They all start with rate, but they mean very different things. The question was, for those at home, do the exponents ever change with temperature? Only really extreme temperatures, for a reason we'll get to fairly shortly when we talk about what the actual molecular interpretation of the orders are. But generally, I mean, if we're talking aqueous, you know, from 0 to 100, or, you know, even 0 to 500, the orders shouldn't change. As I sometimes say, if you go to do it in the surface of the sun, the orders of the reaction are probably very different, for a reason we'll see shortly. So again, the rate is specifically referring to a change in concentration in time. The rate law is really just the functional dependence of the rate on concentration and ultimately temperature through the rate constant, right? And the rate constant, right, is only really constant at a single temperature. It's essentially the temperature dependence of the rate. And so they all have the word rate in them, but they represent something very different, right? And so just from sort of a nomenclature standpoint, right, if that were my rate law, the way I would read it is that the rate is first order in A, first order in B, and second order overall, right? What does that mean? It means it's A to the first power, right? There's implicitly a 1 here. It's B to the first power, right? And second order overall is just 1 plus 1 is 2, right? This is the total of all of the exponents, right? As I sometimes say, that overall order is really redundant, in the sense that if it's first order in A and first order in B, I'm pretty sure you can add 1 and 1, right? But it's sort of an exclamation point, right? Because what it tells me is it doesn't depend on something C, right? Especially if this reaction, right, had a rate law that was only first order in A, even though there is another reactant. If I just said it's first order in A, you're thinking, okay, great. What is it in B? On the other hand, if I say it's first order in A and first order overall, I'm implicitly telling you B doesn't matter, right? And so frequently, this overall order is included kind of as a period or an exclamation point saying, and that's it, kids, right? Questions on that? Anything? Now, people always ask, right? What do the orders mean? You know, there's one very chemical interpretation of it, right? But, you know, if I'm being fair, right, there also is the straight up mathematical interpretation of it, right? It's the functional dependence of the concentration, right? It's the exponent of the concentration. And so in the context of the rate law, there is the algebraic interpretation that it's telling me the strength of dependence on concentration in the rate law, right? It does, however, also have a chemical interpretation. And this gets back to the question we just had from the back as to whether the orders ever change, right? One of the reasons people study kinetics is not because they really care how fast the reaction is. I mean, there's times you do, right? You know, maybe I got a brand new drug and I've got this great simple recipe to make it, but it requires me to cook it for 6 months, right? Well, that better be a really good drug if it's going to take me 6 months to make it, right? In which case, I'm going to try to find ways to make it faster, right? If I'm trying to build a bomb, it has to be a rapid reaction, right? So there's times where I might care about the absolute rate, right? But a lot of the time I measure the rate because I'm trying to actually get the orders of the reaction, because those orders are a way to get specific chemical information about how the reaction's happening, specifically the mechanism for the reaction, right? And so again, kinetics grammar, right? If that's my rate law, right, at the top, the rate is second order in B and second order overall. Notice it does not depend on A, right? Whereas the bottom rate law says, hey, look, the rate is first order in A, it's second order in B, it's third overall, right? So it depends on both A and B, right? Let's assume for a moment, right, that I'm essentially talking about the same reaction, right? One of those is going to be true, right? Because there should only be one rate law. Which one's true tells me something about how the reaction happens. Because if the rate depends on B squared, what that tells me is that whatever A is doing, it's doing it really fast. Because the overall rate didn't notice how much A was present, right? Whereas the bottom rate law tells me that both A and B are doing something that's equivalently slow, right? So ultimately, I'm usually trying to determine the rate law. In part, that gives me a equation I could use to calculate rates for specific reactions. It also gives me information about the specific molecular way that the reaction occurs, right? Which we will hopefully squeeze in on Monday. You know, I don't think we'll have that much time, right? So I normally find the rate law by measuring individual rates. Because again, that's what I've got in the beaker, right? I've got hydrogen and nitrogen and ammonia in my beaker as I'm making, right, ammonia. And so if I'm going to monitor the reaction, that's what I see, because that's all that's there, right? And so as I say, experimentally, I'm usually measuring rates, but I use them as a tool ultimately to find the rate law. And so if we needed yet another term that has the word rate in it, right, what I'm talking about here is known as the method of initial rates, right? Initial rate is really just what it sounds like. It's the rate at the beginning of the reaction, right? There's nothing terribly magical about the initial rate, other than it's the one I'm most likely to know, in the sense that, right, if I were to plot rate versus time, it's doing something like this, right? I mean, it could be doing more like this. It could be doing more like this. That's going to depend on what the orders of the reaction are, right? But it starts at its maximum, and then it is essentially asymptotically approaching zero, right? And so if I'm talking about the initial rate, I'm really just talking about taking a sliver of time at the beginning. Right. There's nothing really magical about that. I could use a rate somewhere else. The only thing that makes the initial rate, sort of the obvious starting point is it's the one place where I actually know the initial concentration. Right. If I want to start timing my reaction, 5 minutes after I mixed everything together, I don't really know what the concentration of anything is at that point. I'd have to go in and measure it. Whereas I always have control over what I put in the beaker to begin with. And so I should know the initial concentration. All right. And so if I'm going to construct the rate law, I essentially, in this case, need to know three things. Right? I need to know what the order of A is. I need to know what the order of B is. All right. And I need to know the rate constant. Right? That is really an experiment spelled out as an equation, right? Because what I really have are three things I need to know. Right? And again, if I'm using initial rates, I actually have two things I should know, right? I need a different color pen, but don't really have one. I mean, I could make one, but it's more time than it's worth. Right? I should know these. Right? You got to be really lazy to not measure stuff before you throw it in the beaker, right? I mean, the one thing you should always know is what you're throwing in the beaker to do the reaction, right? And so I have concentrations I know, and I have three things I need to know, right? Or as you might sometimes refer to them, I have three unknowns. And that's why the rate is the thing I measure, right? It's my actual measurement in the lab. And so I have the two things I measure before I even started anything, the amount of each reactant I threw in the beaker. I'm going to measure the rate, and I want to use that to find the three things I don't know: the orders of the reaction and the rate constant at that temperature. And so one equation, three unknowns. If I'm going to solve it at all, I have to do three experiments, right? I need as many experiments, I need as many equations as I have unknown. Right. It bears saying, because especially once we start talking about equilibrium, this gets confused. There is no way for me to know the orders of the reaction by looking at the balanced equation. It pains me to even put this in a sentence, right? But the stoichiometry does not matter where the orders are concerned. Right. It would if the reaction occurred in one step. Right? This is what I mean by the reaction mechanism. Right? The mechanism is the step-by-step way a reaction occurs. right? It could be that literally 1A and 2Bs have to collide to form 3Cs, right? This is not only, right, the net equation, right? It's the individual step. It's a one-step process. If it were a one-step process, this would be A to the first power, B to the second power. All right. The microscopic chemical interpretations of my orders is that they are the stoichiometry of the mechanism, not of the overall reaction, right? Because reactions frequently, one might even say most normally, happen in multiple steps. And so here's the exact same reaction with a different mechanism. In this case, A falls apart. Why? I don't know. Right? And then the parts collide with the B's, right, to form some kind of reactive intermediate called E. And then the E's collide with each other to form 3C's. Right? If all of those steps happen on the same time scale, right, then the stoichiometry of each of those steps matters. On the other hand, a lot of times there is one super slow step. Slow, of course, is relative. Right. So, I mean, if you think of my journey here, right, I got dressed, that took 5 minutes. I drove here, that took 25 minutes. I had to walk in from the car, that took 5 minutes. That's 3 steps that all took about the same amount of time. Right. In that case, there's nothing terribly rate limiting. Right. On the other hand, right, if I take the same trip to California, right, now it still took me 5 minutes to get dressed. It still took me 5 minutes to walk in the building, but it now took me 48 hours to do the drive. In that case, the 48-hour drive is the rate limiting step for getting to California and going to work there. That's, by the way, one hell of a commute, right? And so since that one step is so much slower than the others, right, the entire rate I measure should only depend on the rate of that step, right? And so the stoichiometry of that step should be the orders of the reaction. If that were the mechanism, my rate law would be first order in B and 0 order in A, because there's no A's in the slow step. All right. I don't spend a lot of time harping on this. The book discusses it more. The OWL homework will discuss it more. Partly because what it's telling me isn't definitive in both directions. What I mean by that is if I go and I measure the rate law and I get the first order in B, it doesn't tell me that's true. It tells me it could be true, right? Because there's probably dozens of other mechanisms I could write that are also only dependent on 1B in the rate limiting step. On the other hand, right, if I thought this was the mechanism and I got this for the rate law, that's not the mechanism, right? And so rate laws are helpful in validating mechanisms, but they will not 100% prove them. They can 100% exclude them if they don't have the right molecularity in the mechanism, but they're not generally definitive, right? Right. And so, again, a lot of times the reason people construct my rate laws is that it gives me some indication of what the mechanism might be. If I get a rate law that's first order in B, then I know the rate limiting step or steps, because again, you could have two steps that are about the same rate, depends only on a B. If I get one A and one B, then it's telling me the mechanism in some way depends on having an A and a B, right? And if I have AB squared, it tells me the mechanism depends on having two B's and one A, right? And so in that case, I really care more about the orders than the actual number for the rate. Right. So returning to actually determining that, right? Again, if I have, from the beginning, I know there's some generic expression. I'm going to go with 3 reactants just because, whoops. Right, if I've got A plus B plus C, right away I know the basic format of my rate law. It might depend on A to some order, or B to some order, or C to some order, or all 3, or 2 of them. There's going to be some rate constant, which is again the temperature dependence, right? In this case now, again, there is no reason not to know the initial concentrations. I'm always measuring the rate. And so in this case, I have, that was a horrible choice, especially if you're blue-green colorblind, right? I have now 4 unknowns: rate constant, X, Y, and Z, right? So essentially, if I'm going to measure the rate law, I always have to do multiple measurements. How many? 1 more than the number of reactants, right? When I had 2 reactants, I had an X and a Y and a K. That's 3 things I needed to know. If I have 3 reactants, it's an X, a Y, and a Z and a K. That's 4. If I had 4 reactants, it's X, Y, Z, and Q plus K, right? And so I'm always going to have to do 1 more measurement than I have reactants in the reaction. And so my data ends up looking something like this, right? For this particular reaction where I have ammonium reacting with nitrite, I have 2 reactants, right? There's also the temperature dependence embedded in K. So I need 3 measurements of the rate to nail down the rate law. And that's what I have, right? Notice all the same temperature, because if I let the temperature change, the rate constants will be different, right? And then these are essentially my initial conditions. And this rate is the thing I actually measured. Right. And so my data consists of measuring the rates all at the same temperature, but for 3 different starting amounts of the reactants. And we'll see how that plays out mathematically on Monday. Questions or problems? Well, it's an intermediate which apparently forms instantaneously because it's a product of the first step. So yeah, we're ignoring the intermediate. And to get back to the question in the back, the reason I say moderate temperatures, right? If I suddenly do that thing on the surface of the sun, maybe my slow step gets faster, right? And so in that case, then I might expect the orders of the reaction to change if I change the conditions extremely. For moderate changes, right? If I increase the temperature, all 3 of those reactions should speed up. And so the slow one should still be slow. Have a
Professor.
good weekend. Stay warm. Yes.
I have a question about the project.
Yes.
So, sorry if I missed this on the assignment, but what should the citation